Okay, so in this last aspect of symmetries, conservation laws, variational problems, we consider a generalization to partial differential equations. We will suppose that the function u is the dependent variable, and that's a function of independent variables x and t. Of course, all these results are extendable to more than one independent variable and to systems of equations. We will notice, or at least we will define our partial differential equation in general to be given by that differential function e equal to 0. Here, for example, then is your classic heat equation as an example in which ut minus u double x is equal to 0. And here are some other classic equations. This one is indicated incorrectly, so I'll rewrite it. That one is u double t. Let's write that subscript better. U double t minus u double x equals 0. That's your standard one wave equation. You've got the Burger's equation, which models shock waves, and then your third order KdV Korte-Vechter-Friis equation, which models shallow water phenomena. And I'm just going to go through a number of the operators that we've come across in the single variable case. For example, if you have two independent variables x and t, there is a total derivative operator now both with respect to x and with respect to t. And they follow a similar pattern. They've been extended here as partial derivatives in the jet space, and they are infinite operators. And when they act on a function, a differential function, of course they are then finite. Most of the terms from some point onwards, the partial derivatives are 0. Moving on, here's an example of taking a total derivative of a function u minus u squared x. So let me just write that a bit better. That is u squared that is u minus u squared ut, or is it ux? That's ux. Okay, so if we're doing the total derivative with respect to x and write it down in terms of partial derivatives, then of course you've got the partial derivative with respect to x of the bracket plus ux, the partial derivative with respect to u of the same thing, plus u double x u double x the partial derivative with respect to ux. Remember, this is in the jet space, so the ux is a variable in its own right, and then you've got uxt, the partial derivative with respect to ut of the same thing. So that's what we will end up with. Okay then, the vector field, of course, in the more than one variable will now be of the type x given by xi, say d dx, plus 1 with regard to the t variable, d by dt, plus phi, say t by du. So that's your basic, based on the basis variables of your one parameter Lie group of transformations, or rather the vector fields that represent the tangent vectors to the one parameter Lie groups of transformations. If we were to extend this or prolong this, for example, to first order derivatives, then there would be a term involving ux and a term involving ut. This is the equivalent of the d by dy dashed. So I'm going to represent the coefficient of dux as phi to the x and phi to the t as the coefficient of d by dut. The vector field is a vector field containing partial derivatives with respect to the various jet space variables. And similarly, if you were to extend to second order, you would include all the second order derivative terms. Meaning, if I were to replace that with a second prolongation, then I would need to include, let's put that in a slightly different color. So there, oh dear, we would have phi double t d by du double t plus phi tx d by du xt or tx, and then plus phi double x d by du double x. So this is your one parameter Lie group of transformation, including the derivative terms. Okay, so if you want to determine the vector fields that leave invariant a differential equation, then we would have to satisfy the two things as we mentioned before, that the left-hand side of your differential equation, which is a differential function, has to be invariant under the vector field, and it has to be along the solutions of the differential equation. The formulae for the phi to the x, phi to the t, etc., in other words, of these things, these coefficients of derivative terms are given very loosely here, but they can be found in any standard book like the one by Peter Olver. So here are the formulae for phi to the x, phi to the t. I suggest you look at the exact clear version in a standard text like Peter Olver's text. So I'm going to go very quickly to this example where we determine the vector fields that leave invariant the heat equation ut minus u double x equal to 0. So first of all, notice the vector field is to be in the function of the left hand side, which is ut minus u double x, which is this function here, has to be invariant under the vector field. So since it's a second order in derivatives, x2 on that function has to be equal to 0, and at some point we will impose the whole differential equation. Right, once you do x2 on ut minus u double x, we get that phi to the t minus phi to the double x. All the other partial derivatives are equal to 0. And putting then the expanded formula for phi to the t and phi to the double x, which are rather complicated formula, and putting that equal to 0, we get this would be on the left hand side, and that would be equal to 0. So all of that is the left hand side. We need to impose the equation. So what we do is we replace all the ut's by u double x. So that would satisfy the second condition, that it has to be modulo or along the solutions of the differential equation. So wherever the ut appears in this expanded formula of the left hand side, you would replace ut by u double x. And then and since the xi, the phi, and the tau are functions of x, t, and u only, the basic variable, the partial derivatives, and these are all partial derivatives in the extended form, the partial derivatives of these unknown functions are also functions only of x, t, and u. So we may separate by first order derivatives, second order derivatives, etc. And we get a system of, again, linear differential equations which form an overdetermined system. again, this example is given in detail, so I suggest you look at Peter Olver's book containing all the details of this, or you look at my lecture notes, which will be presented at some point. So when we separate these and solve for the respective unknown functions, it's what seems to be a detailed procedure, but it's actually quite interesting that it's once you've cleared up all the calculations, you get some nice forms of your vector fields. So it turns out then that the final form of the coefficients tau, xi and phi are given by these, where the alpha i's, a, b's are all genuine constants. And we do exactly what we do before, and that is that we let each constant equal 1 at a time and the rest equal to 0, and we generate all the basis of the vector fields that leave the differential equation invariant. And it turns out that, for example, we end up with vector fields like d by du, xt by du, etc., etc. And here's almost a complete class of vector fields. You notice there is the scaling vector field there, and there's some that are not so geometric. And there's a scaling in u, which is d by du. There's translation in time. There's translation in x. In a variational system, translation in x will be associated with conservation of linear momentum, and translation or invariance in t will be associated with conservation of energy. But that is another story. We do have one vector field that is regarded as an infinite vector field. In our calculation, it turns out that one of the vector fields is an arbitrary function, well, not an arbitrary function, a function of x and t, d by du, where this function, alpha of xt, satisfies the heat equation itself. So any solution of the heat equation, for example, alpha equal to 1, or alpha equal to t plus a half x squared, all solutions of this heat equation give rise to additional vector fields or symmetries of the differential equation. What is different between, in fact, in some senses easier or less cumbersome in reducing, what is different here compared with ODEs is the reduction of PDEs. One need not determine the first prolongation. One needs only the zero order invariance of the vector field, and one can write the partial differential equation in a reduced order. Reduced order for partial differential equation means reducing the number of independent variables. So this, having started off with 2 independent variables, so any reduction of this differential equation, this partial differential equation, will be, of course, a differential equation in 1 independent variable, namely an ODE. Right, so one can then construct various kinds of solutions. You've got if you take a combination of translation in time and space, you end up with a traveling wave solution. So for example, this vector field here, d by dt plus a constant times d by dx plus 0 times d by du. If you write this in a characteristic form, trying to determine the invariance, we write dt over 1, dx over c, and du over 0. Since du is over 0, v equal to u is one of the invariants. That will be the new dependent variable. And when we take a combination of this, we end up with an invariant, which is your integration constant being that. And now we'll write the partial differential equation, the heat equation, in terms of v and y. we replace all the variables and the partial derivatives and end up with a differential equation that was rather straightforward, and we end up with the reduced differential equation in this form here. Now we notice it's reduced in the number of independent variables, which is now 1, and this, it turns out, is straightforward to solve beyond the reduction, and we end up with a solution of V, and replacing the V's and the Y's, we end up with a solution, traveling wave solution of the heat equation. You could take other combinations of the vector fields. Here's one taking a combination of the space and time dilation, scaling, and the U scaling. Add the two and we end up with a vector field of this type. And the invariants are determined by dx over x, dt over 2t, and du over 2au. We just chose 2a as a convenient constant, because any linear combination of vector fields is a vector field that leaves invariant the differential equation. So taking the first pair there, we end up with an invariant of that type, which will serve as the new independent variable, and then taking the combination with u and t, and that we sort out in there, and we end up with a new invariant there. So y serves as the new single independent variable, v serves as the new dependent variable. We write out all the derivatives that appear in the differential equation, namely ut and u double x. U double x is of course via ux, in terms of these new variables. That's ut and that's u double x, and substituting back into the equation, we end up with a single differential equation of second order, but in a single independent variable given by that. So there's the reduced partial differential equation, which is an ODE in essence. It's not always the nicest reduction, but nevertheless it is a reduction. Then looking at the notion of calculus of variations. In the calculus of variations, of course, we will be optimizing an integral. In this case, it is a multi-integral over some region, and the integrand, which turns out to be a Lagrangian eventually, could be a function of x du, and if you keep it to first order, it will be ux ut. The solutions of this variation problem, that means the functions that optimizes an integral of this type, again can be obtained by a corresponding Euler-Lagrange partial differential equation. And in this case, the partial differential equation, perhaps I'll repeat it here, has the form d by du on L minus total derivative with respect to x dl du x minus total derivative with respect to t, partial derivative of L with respect to ut equal to 0. So this is the Euler equation, or Euler-Lagrange equation, whose solutions provide solutions for the corresponding Euler-Lagrange equation. And then the notion of, in the same way, the inverse problem would be, given a partial differential equation, can we find a Lagrangian such that the form of the partial differential equation is this Euler form? There's a large class of partial differential equations which are not variational, i.e. Lagrangians do not exist. Then the definition of a conservation law for the multivariable case. So a vector t to the t, t to the x. Sometimes I refer to it as t and s, is said to be conserved, or is a conserved vector or a conserved flow if the closed form there is satisfied. That is the total derivative of t to the t with respect to t plus the derivative of t to the x totally with respect to x equals 0 on the solutions of the partial differential equation. As before, we could take a Lagrangian and find the vector fields that leave invariant the action integral, and it turns out, as in the ODE case, a vector field that leaves invariant star for a given L, where the vector field is as before given by that vector field would satisfy this equation if we consider a gauge term, but of course here the gauge term would be a vector. We associated f with the x variable and g with the t variable, and hence this form there. So the Noether symmetries, the vector fields that leave invariant, this action integral satisfies that. By Noether's theorem, for every vector field that's a Noether symmetry, sometimes referred to as a variation symmetry, that leaves invariant this integral and the gauge term, gauge vector fg, we can find a conserved vector by formula. And this is the formula, and this is Noether's theorem for the two independent variable case. And here's an example of a Lagrangian of a Gordon type equation. So let me just show that if this is a Lagrangian, the corresponding partial differential equation for which this serves as a Lagrangian would be, if you did the Euler operator on L equal to 0, you should get u double t minus u double x plus u cubed equal to 0. So that's a partial differential equation whose Lagrangian is that. We find the vector fields x for which the action integral is invariant, i.e. we go through this, and in this case I've chosen the gauge vector to be equal to 0. So f comma g is equal to 0. We go through the calculations, we end up with three vector fields, d by dt, d by dx. This is translation in time, translation in x. So this represents energy. This one, linear momentum. And we've got, you notice t dx plus x dt. This looks like a rotation in time. So this is your pseudo rotation. This is sometimes called the Lorentz rotation, which represents conservation, the spin conservation. Once we know the vector fields, each of these vector fields, x1, x2, x3, and in this case they're all zero gauge, you plug these into, with the L into Noether's theorem, you end up with a corresponding conservation law or conserved vector. So for example, if we choose x3, which is one of the Noether symmetries in which tau is equal to x, psi is equal to t, and phi is equal to 0, plug it into Noether's theorem for t to the x and t to the t, you have a conserved vector. And this is the check for that. Here is another example of your Klein-Gordon equation. You may go through this. This is the one with detailed calculations also, and it turns out that one ends up with similar vector fields. And this one, of course, we assumed a possibly non-zero gauge vector, and the non-zero gauge vector produced an infinite symmetry there too. And that's Noether's theorem applied to those Noether symmetries to give us the corresponding conserved vectors.